So we're looking at this, okay? So we just define how you can take the Laplace, alright? And remember that this is a special thing. What we are trying to say is that the Laplace operator, okay, is a linear operator. It means that if you have a lot of functions like that, then you can take the Laplace through, okay? So the Laplace operator is a linear operator, as in that of an integral, which is also a linear operator, okay? So take note. Now, so this is a table, a Laplace table that has various functions and then their Laplace transforms, okay? Various functions and then their Laplace transforms. So when you have a 1, the Laplace transform is 1 over x, okay? So when you have a 1, the Laplace, so if your f of x, f of t, your function, which are saying f of t, is just a function which is a constant, let's say a constant c, alright, then the Laplace of this is just the integral. You are integrating from 0 to infinity, alright, e raised to the power minus xt, alright, and now the function which we are looking at is just a c and then dt, alright. So this is what we are trying to solve. So when you solve this out, you only have negative e raised to the power minus st, alright, divided by x, and then you are trying to put a naught and then infinity inside this expression, and remember your c will come up, alright. So when you put a naught inside, it goes to 0. So when you put a 0 inside, it goes to a 1. So all what you have here is that we have c over s, okay. So when you are taking a Laplace transform of any constant, it's just a constant over x. So in a way, if I'm taking a Laplace of a 1, it's just a constant 1 over s, okay, constant 1 over s, alright. So that is basically what you do. So there's a Laplace transform of e raised to the power at, okay, which is given as that. So even if you don't have the techniques at hand, you can actually go through that, but you can try proving everyone, which any of these ones, okay, try proving that. So if you have a Laplace transform of t raised to the power 2, alright, so you want to look at the Laplace transform of t raised to the power 2, right? You want to take the Laplace of this guy. So per this formula, what you have is n. So this is n, the power is n, so you need n factorial. It means that I need 2 factorial or divided by, alright, s raised to the power n, so s raised to the power 2 plus 1, okay. So that will just give me 2 factorial is 2 over s raised to the power 3, alright. So that's going to be the Laplace transform of t raised to the power 2. So you can do that for t raised to the power 3, t raised to the power 4, t raised to the power 5 in that order. If you want to take a Laplace transform of e raised to the power, let's say, minus 6t, alright, this is what you're going to take the Laplace. How do you do that? He's saying that you only have 1 over s, alright, minus, what is a? A is what is in front of t. So in our case, a is minus 6. So minus, alright, there is another minus 6. You close it. So that is going to give you 1 divided by s plus a 6, alright, s plus a 6. So that's how you take the Laplace of exponential functions. This exponential function and this is a power function, alright. So you take the Laplace through this technique. So these are various it's a table, so you have to know all of them. You can just capture that table and then study them. All right. So this is how it is done. Okay, so you see that the rows of table 1 can be determined by whatever. So what we are saying is that if you take the Laplace of e of t and then a function of, now if you take a function, if you are taking the Laplace of the product, okay, product. So what we are saying is that if you have e of at, we know its Laplace, isn't it? We know the Laplace of this guy. We know the Laplace of this guy already, all right? Which is what we said is 1 divided by s minus a, isn't it? All right. Now this is a. So, right, so s minus a, but what is the Laplace of multiplying that expression, which we know its Laplace, by any function? Okay, so when you multiply the e by any function and you take the Laplace, what happens is that you shift the Laplace of f of t by a. Okay, you shift the Laplace of f of t by a. So what happens is that if, example, I have e raised to the power 4t, all right, so this is exponential, and I multiply by a function called t raised to the power, let's say, a 3, and I'm trying to take the Laplace of this guy. All what I have to do is that, okay, now what's the Laplace of this? And I'm going to shift that by a 4, right? So that is what has been done here. So what's the Laplace of this? Okay, the Laplace of that is 3 factorial, all right, 3 factorial all over, then I'll have s 3 plus a 1, isn't it? Plus 1. So that means I have 6 all divided by s raised to the power 4. So this is the Laplace of this, the Laplace of t cubed. So because this has been multiplied, to take the Laplace of the entire thing, I just have to shift this s by -4 or by this 4. So the whole thing just boils down to saying that I have 6 over s minus 4, all right, all raised to the power 4, all right? So that is that, all right, that is that. So that is basically how you can take the forward transforms, right? So we'll look at a typical example. This is a table, and then so we'll go through and look at some typical examples. So that